Ladies and gentlemen of BlueHat 2025, trust nothing.
Hi everyone, I'm Yarden. I'm currently a vulnerability researcher for Vigilant Labs. Earlier I worked at Trail of Bits. I've done a lot of EDR development at CrowdStrike and Center01, so I've worked at both sides of the InfoSec industry. I've done offensive work, I've done defensive work, and I've done all sorts of stuff in between. I've been a circus artist, I've been a pastry chef, I worked at a zoo. I've done a lot of different jobs. A lot of them have more to do with security than you would expect. I also teach Windows internals for Winsiders, and I do a lot of public work, talks, blog posts on both offensive, defensive, forensics, mostly focused on Windows. So today, I'm here to talk to you about one of the stupidest bugs I've found. Before I talk about the bug, some history about ASLR, Address Space Load Randomization. Back in the distant past, in Windows, everything was always loaded in the same address. All of your modules and your heaps and your stacks and everything else was always loaded in the exact same address on any system every single time. That meant writing shellcode was very easy. You just needed a way to execute your shellcode, and you could hard code all the function pointers and all the variables. It made heap spray very easy. Exploitation used to be much easier than it is today. And that was true for both user mode and kernel mode. So in user mode, you've had ASLR since about Windows Vista. That's when it started out. It advanced over the years, and now things load at a different address every single boot. A little bit later, KASLR followed. KASLR, kernel address space load randomization, means things in kernel mode load at different addresses. So your kernel modules and your heaps and your stacks and your shadow stacks all load at different addresses that get randomized once per boot. It took a while for everything to get randomized. That happened much later, only in Windows 10. But now, modules and pools and everything else are at various addresses. So what does that matter? Because when you have any kind of vulnerability that requires knowing where something is, if an attacker can't know where it is, it means they now need at least two vulnerabilities to exploit a system. One, to know where the data or code or memory they're targeting is, and a second one, to actually do something useful with it. For example, one of the more common attacks you do when you have an arbitrary override in kernel mode is to patch a pointer. To patch a token. You find the token of your process that is a very unprivileged process. You find the token of a more privileged process. The system process is a common one, but not the only option. And you replace them. You copy the system process token instead of your token. But you can't do that if you don't know where your token is. So you need to find your kernel process structure that we call an e-process. Based on the operating system version, you know where the token will be inside of that. And then using your arbitrary override vulnerability, you can replace it with the address of a more powerful token that you also need to find separately. So over the years, Microsoft decided that maybe user mode processes shouldn't know where things are in kernel mode. From user mode, you don't have direct access to kernel mode. You should not be messing with kernel mode data. If you're messing with kernel mode data, it means some vulnerability happened. So why even give you kernel mode data to begin with? So recently, there is a few different mitigations against user mode attackers in kernel mode. A slightly older mitigation is restricting who can get kernel pointers from user mode. So for context, Windows makes it pretty easy to get kernel pointers, at least some of them. There's APIs that are partially documented that will just give you kernel pointers. For example, NT query system information with some of its information classes will give you the addresses of objects or the addresses of modules. So these are well known. And for a few years now, those have been restricted. So you can only call them from a medium integrity level process, which is a normal process. It means you can't call them from a sandboxed process, from most browser or Office processes. But if you're running as a regular application, you can still call them and you can still leak kernel pointers, which is still not great. So more recently, Microsoft decided to harden those restrictions. And now, to call any of those APIs, you need to run as an admin process with a special privilege called SeDebugPrivilege. That privilege is not enabled by default, but if you're an admin or system process, you can enable it. If you're not a process running with debug privilege, you can still call those APIs, but you will not get back kernel pointers. You'll get back other pieces of information, but any field that used to have kernel pointers will now be zeroed out. The second mitigation is telemetry. There is a new ETW event in the threat intelligence ETW channel called the syscall usage event that is not specific to KASLR. That is an event that Microsoft designed around APIs that are known to be linked to exploits. Calling those APIs isn't necessarily an indicator of malware, but there is a high correlation between those APIs and exploits. So any call to those APIs by a process that is not running as admin will generate this event that EDRs can choose to subscribe to and add that to their whole detection model. So great, no more kernel pointers, at least not any that are known. There were a lot back before one of the later Windows 10 updates. Win32k, unsurprisingly, leaked a lot of kernel pointers and some other vectors too, but those are all gone. Great, no kernel pointers. Well, there's still some kernel pointers. So this is what I call one of the stupidest bugs I found. You open Event Viewer, at least on a system that hasn't been patched, and you look at ETW channels like NTFS, or like a couple of the Hyper-V ones, and you see kernel pointers. Now, you don't get to choose which kernel pointers. Each one leaks slightly different ones, depending on how they were written, but you definitely get kernel pointers from user mode. Well, good thing you need to be an admin to get those kernel pointers. ETW events get written to a file on disk. Those files are in a protected directory, the logs directory, that, at least based on the security descriptor, you need to be either an admin or system or local service or the event log service to read those logs. Local service and event log service are also very privileged, also more or less equivalent to being an admin or system, so that should not be a problem. If you're at those levels anyway, you can get any kernel pointer you want. So this is not really a bug, unless you can read those without being admin or system. So here I have, I don't really do live demos because my computers hate me on a personal level. So we have a screenshot. You'll just have to trust me that I didn't fake it. PowerShell running as a completely regular, non-elevated user, reading those event logs. This time, I read the NTFS log, where you get a kernel pointer of a structure called VCB, a volume control block. Then I created a low-integrity PowerShell. So a PowerShell process that doesn't even run as a normal medium-integrity process. It runs as a low-integrity process, like most browsers would. And still, I can query that. I can get the address of the BCB. I can query any of the vulnerable event logs. Now, this is where, if this was a different talk, I would tell you about the really cool OD I found that allows me to run as a low-integrity process and read a file that says you have to be an admin or system to read it. Unfortunately, I don't have one. There's no OD. Everything is working exactly as planned. Everything is working based on the normal Windows security model. PowerShell can just read this file, even as a low-integrity process. But it can't read it directly. If I wrote PowerShell code that just calls create file to open those files, I would get the same access denied error that you would expect me to get because it is not a strong enough, it's not a powerful enough process. So if PowerShell doesn't read this file directly, what happens? Well, there's a service called the event log service running as NT-service event log. This service is allowed to read and write to all event logs and can choose to do that. And PowerShell just very nicely asks this service, hey, can you read this event for me? Now, PowerShell is a pretty high-level process, so you don't really see that happening. But what actually happens is that the event log service has an RPC port. RPC is an IPC mechanism, an inter-process communication mechanism that allows processes to talk to each other. And RPC is always really interesting because it allows processes to talk to each other across different privilege levels. A low privilege process can talk to a system process. A browser can talk to a kernel driver. And RPC has had a lot of vulnerabilities over the years, some in RPC itself or any of the mechanisms that are underneath RPC, and some in the way it's implemented. If a process has an RPC port that allows an unprivileged process to do something it shouldn't, that is a logical bug, which I think is the best type of bug. And those can be hard to find because those are not generic bugs. They are specific to a specific RPC port, to a specific implementation, to a specific function. In this case, the non-vulnerability is the fact that this port has a query function that allows any process with access to the event log port to read any event log that the event log service allows it to. And really, the only event logs that you are not allowed to read as nearly any process are the ones that are tagged as admin ones. If you open the event viewer application, you'll see some logs there that are admin logs. There is a check there whether you're an admin or not when you try to read those. In any other case, almost anyone is allowed access to the RPC port. So I think I have it here. There we go. So here is the security descriptor of the event log RPC port. We can see that on my left, everyone is allowed to connect to the port. Over here, we see that all application packages are also allowed to connect to the port. All application packages is the group that Microsoft uses for all app containers, one of the many sandboxing technologies that Microsoft developed. So even as an app container from a browser, from anything else that uses these sandboxes, you can still connect to the event log service. It doesn't mean you're allowed to do everything you want, because there's different functions supplied by this RPC port. So there is query, there is read, there is write, there is delete, there is clear, and each one of them makes its own decisions about who is allowed to do what. Now this is where we have another part of the Windows security model, and that is how it handles integrity levels. So objects can also have integrity levels, low, medium, or high, mostly. And in the Windows security model, generally, you are only allowed access to objects that are in the same integrity level as you or lower. A process can't write to a process that is more privileged than itself. A medium integrity process can't write to a high integrity level process, but can write to a medium integrity level process. So this RPC port was created by a high integrity level process. It does have an integrity level, but still anyone can query it. That's because query by Windows is declared as equivalent to read. And in Windows, you're allowed to read up, meaning in almost all cases, a process is allowed to read from an object more privileged than itself. The only exception here is processes. You're not allowed to read from a higher integrity level process, but you are allowed to read from an ALPC port, in this case, an RPC port. So if you can query that, you can open this RPC port. You can query any event log that is not a dedicated admin event log, and you can get kernel pointers. So all this is a pretty dumb bug. You just open the event viewer and you see the kernel pointers there. This is also a really, really useful bug because of a few reasons. First of all, it bypasses pretty much all telemetry. Even before the syscall usage ETW event, a lot of EDRs and security and monitoring products hooked the dangerous or suspicious APIs and still had those as part of their security model. This doesn't go through any of those APIs because no one calls the anti-query APIs that leak kernel pointers because they don't come from there at all. They come from a file on disk that the process doesn't open directly. It doesn't read it directly. The event log service reading event logs is not a suspicious operation, so it doesn't raise any suspicions. Also, EDRs don't have a mapping of which kernel pointers are leaked where, first of all, because until recently it wasn't really a known thing at ETW events, leak kernel pointers. So there's no telemetry for that at all. It doesn't raise any flags or anything. This is allowed to any process, low integrity app container, any process at once. And the coolest thing about this is even though the specific ones I found and reported were fixed, and there were 6 CVEs here, over 3 different event log channels. There were just different events that leaked different pointers. Even though those were fixed, there's no guarantee other ones will not come back, because this is not one bug. This is multiple bugs. There were kernel pointers leaked in the NTFS channel, in a few of the hypervisor channels, and each one of those came from a different driver. So driver developers, when they write their telemetry through ETW, they design their own ETW channel, they design their own events, and they choose what to write there. So independently, a few different driver developers chose to write kernel pointers to their ETW events. There's no guarantee there aren't other drivers, Microsoft or third-party drivers, that do the same. And even though those specific cases were fixed, there's no guarantee they will not come back in the future, because unless all event logs become admin only, or unless there is some review process that happens, or there's any automated fuzzing or automated testing that makes sure no kernel pointers are ever leaked, this type of bug will probably come back sometime in the future. Also, the fact that I looked at the event viewer doesn't mean this is the only vector that leaks kernel pointers. There is a lot of other interfaces that connect kernel and user mode applications. So event log is one of them, but there's a lot of different RPC ports that are shared or linked between kernel and user mode. Any one of them could be leaking kernel pointers. Pointers could be leaked in log files, or registry keys, or named pipes, or any other IPC mechanism. Also, I was looking for kernel pointers because that's what interested me at the time. But if any process can read almost any ETW channel, maybe there's other interesting information there. Maybe there is private information shared from certain applications that other applications can read. Maybe there's private data, passwords, financial information. Anyone who sends an ETW event decides what that looks like, and that can come from drivers, that can come from services, that can come from third-party applications. So there is no guarantee there isn't a lot of interesting information shared here that attackers can use from a low-integrity process, from an app container, from a browser. So, a few things to take away from this talk. Very first thing, which is true across any talk you'll hear, is don't trust driver developers. Not as people, not as developers. Last summer, there was what some of you may remember as the big blue screen incident. A driver made a mistake, a lot of things crashed. So drivers making mistakes, or driver developers making mistakes, can be pretty destructive and can be very dangerous functionally, or from a security perspective, from a lot of different angles. So trusting individual driver developers can be risky because you don't really have any control for what they'll do. And kernel pointers will keep being leaked as long as there are drivers that can pass any information from to user mode, because you really can't control what happens across all drivers. You can't even control what happens across all Windows drivers, because there's a few hundreds of them at best. And you definitely can't control what happens across the entire industry with tens or hundreds of thousands of drivers out there. Second, look for new attack vectors. There's always new vectors. Where there is anything crossing a security boundary between user and kernel, between browsers and regular applications, between virtual trust levels across VMs. Where there is a security boundary across, there will be vulnerabilities. And sometimes those vulnerabilities are much less complicated than you'd expect. Sometimes they'll just be right there, right in front of you. One more thing to learn here is that RPC is really cool, and RPC is really dangerous. And even though there have been a lot of vulnerabilities already discovered and patched in RPC or around RPC, there's always more. And even areas where vulnerabilities were already discovered and fixed does not mean new vulnerabilities are not going to show up. I fully expect new kernel pointers to show up in event logs in a year, in 2 years, because this will not get tested properly, this will not be validated properly, or there's just drivers that haven't been fixed yet. So, running a bit faster here on time, so I won't use my entire time, but just general conclusions. Don't trust drivers, look for new attack vectors, and don't disregard attack vectors that might be just right there in front of your face, because sometimes it is much easier than you think it is. So, thank you all, and I hope you have a good BlueHat.